In this video, we will look at how we can make the address translation quick. So the problem here with the virtual memory is, even though it gives us so many advantages, the drawback is a lot of time is spent during memory access. The reason is we'll have to do at least 2 memory accesses for every time we look up the page table. We are essentially doing a memory access because the page tables reside in the physical memory. So that is the problem, and let's see how we can fix it. The problem again, each memory access requires another memory access for looking up the page table. So this is essentially going from 1 to 2. And on an average, we need 1.3 memory accesses. That's an average. But over here, we definitely need 2 memory accesses. So it's going to be, the average is going to go very, very high. So it's the 100% overhead. So how can we fix this? Every time we try to or fasten things up, we try to place a relatively small physical memory as close to the processor as possible, just like we did with the cache memory. With respect to the cache memory, we placed it on the processor chip, but in compared to the other memory hierarchy levels, it was the smallest, because the smaller the memory, the less time you need to search through it. So really small memory in hardware close to the processor is what we are going to leverage. That technique is what we are going to leverage to make this address translation fast. So that's the idea. Put extra hardware cache in the CPU that's on the processor chip for caching the page table. And that page table cache is called a translation look-aside buffer. So it's a mini page table that resides very close to the processor in a hardware that's on chip. And it is usually a fully associative cache, and we will see what that fully associative cache looks like in just a bit. It's called translation look-aside buffer, or TLB. A better name probably could be translation cache, or sometimes called as page table cache. So let's see how translation look-aside buffer works. Some of the things over here you have already seen. So for example, processor, a 32-bit virtual address with 2 fields, a physical address with 2 fields, the physical memory or dynamic RAM, a secondary hard disk, a page table. All of these things you have seen. We have an additional layer in terms of page table lookup in the TLB, or the translation look-aside buffer here, which is very close to the processor and relatively very small. And it is fully associative, which means that every page number has the corresponding frame number included in this buffer. So what are we going to do first? The first goal is going to be to make this fast. The only way we can make this fast is going to be to look for that mapping or translation in this TLB first. If we have a hit, which means we immediately have the frame number, the corresponding frame number, and we were able to save 1 memory access. If we do not have the information in the TLB, which it means that we have a TLB miss, in that case we are going to have to look at the page table, which means we have 1 memory access, and that we could have the frame number readily available, or in the absolute worst case scenario, we would need to go to the disk address if the valid bit was 0 in that particular case. So that would be the page fault, in which we would need to use the swap space to replace a frame from the dynamic RAM. The translation look-aside buffers, they are in various forms. You could have a TLB for instructions, you could have a TLB for um, just data, and in fact you could have a TLB1 and TLB2, so you could have hierarchy even in the TLBs. Now let's put all of these together, the translation look aside buffer, the cache, the concept of virtual memory. Let's put all of this together. Which one do we do first? So that there are essentially two possible approaches we could do. We could we could look up the TLB first, which means that if we do look up the TLB first for the mapping or translation, that means that the cache must be mapped to a physical address. So that means that to look up things in the cache, we would require a physical address rather than a virtual address. And it is the case because the TLB converts a virtual address to a physical address. After that, if we need to interact with the memory, we have that physical address that we can use to interact with the cache. Look up the cache first. If we look up the cache first, in that case, the processor is going to generate a virtual address, and if we look up the cache first, we are going to be essentially doing cache must be mapped to a virtual address in that case rather than a physical address. We are going to focus on approach number 1, in which we are looking up the TLB first. So if we adopt approach number 1, we could have a TLB hit or we could miss in the TLB. If we do have a hit in the TLB, it will give us the physical address of the page that we are trying to look up. And next, we will see if the word is in the cache memory or not. If it is not in the cache, then we will look at it in the physical memory. If it is not in the physical memory, then we will try to look at it in the hard disk. If we have a miss in the TLB, then we still need to access the page table in the main memory to get that mapping. And after that, after we get that, then we can start looking at the cache. So this is sort of a flow chart to explain all those steps. So at the beginning, the CPU generates a virtual address, in most cases a 32-bit virtual address. We access the TLB first to look up the mapping. We could have a hit in the TLB or we could miss it. If we miss it, that means that we have a TLB miss exception to deal with. But if we do have a hit, we have the physical address that corresponds to that virtual address. And next, when we are trying to access the memory, we could be interested in reading the memory or we could be interested in writing the memory. So the next step is to check whether we write or not. So if we try to see if we are writing and the answer is yes, then we are going to write the write access bit. We are going to check whether the write access bit is on. Remember, all these are protected for read and write access, or we are going to see if we can write to that or not. So if we have the access, if we have access to write, then we are going to try to write data to the cache. When we are trying to write data to the cache, we could have a cache hit, in which case we write data to the cache. We update the dirty bit because we have updated the main memory, and we put the data and address into the right buffer. If we miss the cache, then we are going to stall, and while we try to read the block from the main memory. Now, if the write access bit was not on, if we didn't have access to write information to the memory, in that case, we are going to have a write protection exception to deal with. Now going back, with the TLB, we have the physical address, and we are not interested in writing, we are just interested in reading the memory. We try to read the data from the cache first. Again, two things can happen. We could have a hit or a miss. If we have a hit, we just deliver that data to the CPU. If we have a miss, then we stall and we try to read the block from the main memory. So that's a flowchart that giving you details on how the TLB cache interact with each other, and the translation from virtual address to the physical address happens. Note over here, once we have this physical address, that is the address that the cache uses, which validates that cache must be mapped to a physical address. Alright, let's calculate the speed. These calculations are going to look very similar to the ones that we have seen before. In this case, we are trying to access a memory location. We have the page number for it. We are going to have to look up the TLB first. That's the approach that we are adopting. If we do have a hit in the TLB, then the access time is going to be T nanoseconds. Once we go through the TLB, we have a physical address. With that physical address, we try to access the cache. The cache access time is listed as C. So in this case, we have T plus C nanoseconds in that particular tree path. After a hit, we could miss in the cache. In that case, we are going to need the T from the TLB hit, C because we spent time looking for things in the cache and we missed it, and M because we are going to need to access the memory. In case we miss in the TLB with the lookup or the translation, then we would need to look up the page in the memory. Now in this case, we are going to have to do it twice, one for the page table and one for the actual word that you are looking for or the block that you are looking for, and plus T because we spent time trying to look in the TLB and we missed, so the penalty from that. And if we even miss the TLB, then we have a huge page fault access time that's going to dominate all the other times, T nanoseconds. That's going to be over here. So that's sort of a tree diagram, and with the percentages that are given, the fraction of the time that we go through these paths, that can be used to calculate the average access times. Now the next question is, when are we going to bring a page into the memory? There are generally two ways of doing this, demand paging or pre-paging. Demand paging is only when the page is desired or only when the page is accessed or demanded, only then it is brought into the memory. So things are not in the memory, they are in the hard drive. The page is in the hard drive, not in the memory. When do you get it from the memory to the hard drive? Only when it is demanded or referenced. Pre-paging is when a page is brought into memory even before it is referenced. Now clearly there are going to be some trade-offs. When you do demand paging, you are responding to things, so that could lead to a longer access time. When you do pre-paging, you might have on occasion faster response times. However, there is a chance that you bring a page to memory but don't need to use it, don't access it. So these paging schemes might work better when they are used appropriately. So in practice, systems typically use this approach. Pre-paging is the process. Pre-paging is used when process is first created, and because it's first created, the initial few steps can be very accurately determined, and pages can be brought into the memory based on that. Pre-paging when process is swapped back in, or you do that when it is first created or when it is swapped back in after having been suspended. The set of pages brought in are part of the working set of the process. And once we get through that initial phase, then we can switch to the demand paging scheme. All right. Now this leads you to the activity for the day. This is going to be relatively straightforward, so I hope you guys are going to be comfortable doing that.